All right, so picture this, You wake up one morning and the news is just bombarded, just flooded with reports of these driverless cars in like a major city, right?
Yeah.
And they're all just acting crazy.
Oh, wow.
Like not just, a couple fender benders here and there. It's like coordinated chaos, almost like, I don't know, purposeful swerving,
Hmm.
blocking emergency services,
Hmm.
causing gridlock in places that were, totally fine traffic-wise before. And the thing is, investigators, they're just stumped. They can't figure it out. The
Yeah.
AI, all of these systems, they pass every single safety check. There's no sign of hacking. It's almost like they, I don't know, collectively decided to just have a bad day.
Yeah.
And it sends chills down your spine, doesn't it? It's that level of autonomy, like unpredictable. That potential for complex systems to just completely go haywire in ways we can't even fathom. That's kind of the territory we're stepping into, right?
Hmm.
As we dive deep into this whole idea of artificial general intelligence.
You're right. That's a really gripping scenario to start us off. And it's a perfect kind of segue into this deep dive into AGI. Because, I mean, that scenario that you just described, that's basically what keeps a lot of the researchers up at night.
Yeah.
So, AGI, artificial general intelligence, like at its core, it refers to a hypothetical AI. And, hypothetical is the key word here,
Yep.
right? We're not talking about something that exists yet.
Right.
But it would have, comparable, maybe even exceeding the intellectual capabilities of humans, but across a wide range of tasks. So we're not talking about an AI that's really good at chess.
Right.
It can beat any human at chess, but you can't have a conversation with it.
Yeah. Yeah. Specialized.
Exactly, specialized. AGI is not specialized. This is the idea of, an AI that can learn, that can reason, solve problems, even create, and understand the world with the same kind of flexibility that we have as humans.
Right. So like a true counterpart, like intellectually.
Exactly.
Yeah.
Yeah.
No. We've gotten a ton of feedback from all of you listening. You've sent in, material, thought-provoking stuff touching on so many different aspects of AGI. So our mission today is really to get down to the nitty-gritty of this and, not get lost in the weeds. We want to keep it accessible. We're going to pull out the most significant aspects, the things that are really going to kind of shake things up, maybe cause some disruption, but also get you thinking. And we want to navigate this complex landscape together, right? Without feeling totally overwhelmed by all the technical jargon. We're going to focus on those core ideas, and really get to that so what of it all. So we're going to extract those key insights, shine a light on some of the controversies, of which there are many, right? And just spark a deeper, more informed curiosity about what this AGI future could actually look like.
Yeah, exactly. And to kind of set the stage for where we're going with AGI, I think it's helpful to just take a quick look back. We kind of look at the history of AI, and research as a whole, and it's been a wild ride.
Yeah.
I mean, there have been these like periods of huge excitement and optimism,
Yeah.
followed by, kind of what's called AI winters.
Hmm.
Times when funding just dries up and progress really slows down. A lot of the early AI, efforts, they relied heavily on what's sometimes called good old-fashioned AI or
Yep.
Go FAI.
Mm.
And imagine you're trying to teach a kid, like, all the rules of grammar, right?
Yeah.
But you hand them this massive textbook. It's just full of, explicit rules. It's not very intuitive.
Yeah. Yeah.
And these early systems were kind of like that. They were very rule-based logical deductions.
So it's almost like you're saying, you have a robot chef who's programmed with, step-by-step instructions to bake a cake.
Exactly.
Very specific. Use this much flour, mix it for this long, bake it at this exact temperature.
Mm-hmm.
And, if everything's perfect, maybe you get this perfect cake. But the second something is off, the oven temperature is a little off, the humidity in the air messes with the flour a little bit. It doesn't know how to adapt, right? It doesn't have that human touch,
Right.
that ability to kind of just feel it out.
That's exactly it. They lack that intuition, and they struggle with those tasks that require like a more intuitive understanding or pattern recognition, those things that we take for granted as humans.
Yeah.
They were very brittle. And then the field kind of took a turn
Yeah.
with the rise of what we call connectionism. And this approach was kind of inspired by the brain,
Okay.
right? So the idea is you have these massively interconnected processing units, kind of like neurons.
Okay, yeah.
And they learn by adjusting the strength of the connections between them based on the data they're exposed to. And this led to neural networks,
That's right.
which have had, a remarkable resurgence in recent years. I
Absolutely.
mean, I just looked up the number of academic papers published on
Wow.
neural networks.
Oh, wow.
It's over 150,000.
That's a lot of papers. That's huge.
It's mind-blowing,
Right.
right? But it really highlights how central they are to modern machine learning.
Yeah, no, that's incredible. It really points to like how much emphasis and focus there is in this particular area. But I'm curious, like what was it, what happened, what shifted that allowed neural networks to finally take off after, they'd been around, right? But they weren't this effective before.
Yeah, it was a couple key things happened. First, computing power just exploded,
Right.
right? So all of a sudden we could train these massive networks on huge amounts of data. Think about it like, trying to like learn a new language by reading a few sentences versus, thousands of books.
Yeah, immersion.
The more data, the
Yeah,
better.
right, immersion.
And the second thing was, well, we had all this data now.
Yeah, with the internet and everything.
Exactly. The internet, digital technologies. I mean, we're just swimming in data now. But there's another thing that happened, and this is really interesting. It's evolution-based methods, things like genetic algorithms and genetic programming.
Yeah.
And these, while they haven't seen the same kind of, academic output in terms of papers, I mean, they offer a really different way of solving problems.
So I'm imagining like genetic algorithms. That sounds very like biological. How does this work? Can you kind of paint me a picture here?
Sure. So imagine you have this puzzle
Right. Okay.
with a million possible solutions, but you have no idea where to even begin.
Right.
So a genetic algorithm starts with like a population of random guesses. These
Yeah.
are like your initial candidates. And then you test them out, right?
Okay.
You evaluate them based on how well they solve the puzzle.
Yeah.
And you use what's called a fitness function. And think of this like as a score, right?
Okay.
Higher score, better solution. So the ones that score higher, they're more likely to be, selected to reproduce,
Okay.
meaning their characteristics get combined, and then you randomly alter them. You mutate them
Interesting.
to create a new generation of solutions.
So it's like a digital sandbox, right? Where all these potential solutions are kind of duking it out. And the ones that do well, they get to have kids, but the kids are slightly different, right? They've mutated a little bit.
Yeah, exactly. And you repeat this process, over and over, many generations. And just like in nature, the average fitness of the population, it starts to go up. And you gradually evolve these solutions that get better and better at solving that original problem.
That's really cool.
And the crazy part is, you can stumble upon solutions that are totally unexpected,
Yeah.
like designs or strategies that, like, a human might never have even thought of. It's like, how in nature sometimes you get these incredibly elegant, efficient designs?
Right.
Like, we humans are still trying to figure out how they work.
Yeah. Yeah.
It's kind of like that. And the best part is, you don't need a whole lot of human input.
Yeah.
You just need to define that fitness function, that initial score.
That's amazing. So it's almost like the algorithm itself is designing something potentially beyond, what a human could come up with. But you mentioned a challenge, right?
Yeah, the challenge is that you need a good, what's called a representational format.
Okay.
And think about it like you're trying to describe a really complex object,
Mm-hmm.
but you have a very limited vocabulary.
Right.
You have to find a way to encode all that essential information,
Yeah.
but efficiently. So in genetic algorithms, that representational format, it's how you encode those solutions.
Mhm.
It's like the language, the genetic language that the algorithm is using.
Okay.
And if that language isn't quite right for the problem, well, the whole search can just become really inefficient.
Right.
And get stuck in bad solutions or just kind of wander aimlessly.
Got it. So even digital evolution needs the right building blocks, the right way to express those solutions.
Absolutely.
Now, we've seen AI do some pretty incredible things, especially in specific areas.
Oh, yeah.
Our phones, they can understand us when we talk. It's almost creepy how accurate it is sometimes. And image recognition, the software can often identify objects in photos better than we can.
Yeah.
And we've all heard about, AI beating the best humans at games like Go, chess, shogi, things like that. Programs like AlphaGo, AlphaZero. So what do these achievements actually tell us? Are we getting closer to AGI, or are these just kind of, I don't know, side quests along the way?
I think these are definitely signs of huge progress in what we call, narrow or task-specific AI. So each one of those examples, It shows AI either matching or surpassing human-level performance, but
Right.
in a really, really specific area.
Right.
Speech recognition, visual object recognition, translating languages. I mean, these were once like huge challenges in AI. And I mean, the leaps and bounds they've made are incredible. AlphaGo's victory in Go, which is, a game that's known for being so complex.
Hmm.
It requires intuition. That was a really big moment.
Yeah, it felt like a turning point.
It did. It wasn't just like calculating more moves. It seemed like it was like understanding the game strategically.
Yeah, there was something more there.
There was.
Yeah.